to extrapolate anything in the observed data space because your data is discrete. So the condition independence relationships from this graph extend to the Poisson rates, but not to actual observed samples, right? So this is as far as we can go. So this graph has value. However, I would not put my money on it because there are so many graphs that look the same and they essentially receive comparable posterior probability, right? So that's what you get out of these models. So you get what I promise you. However, you get what I promise you, a graph at the constant levels with high uncertainty, right? So now there's one slide that I skipped here. See, and these slides represent the results of using all the data and looking at coverage rates and mean lengths of 95% credible interval. So you see here that, so that's Alan Gelfand's model. So Alan's model, has a coverage rate of 0.99. That is less than ideal because you should get 0.95 or something close to that. And you see our three other models that make use of the G-Wishart distribution, right? So this model again doesn't include any condition independence relationships at the column level or constant level, but still uses the G-Wishart prior to impose spatial dependencies, right? Even that makes a huge difference, right? And in terms of the mean length, both of these models do better than the other two. So that other step was also needed, right? So those are the results, you see. So they are meaningful, and I have a couple of other. How much time do we have? 5 minutes. Okay. So I have another example here. This is a simpler example, you see. So the data set now is a matrix that's 49 by 2. The column-wise dimension relates to the math and verbal SAT scores, right? And you see here the dependence you get between those scores, right? So it's a clear dependency. So you would expect a relationship between those scores to be there. So now if you use this machinery, what you get at the end of the day is you have one graph with two vertices, right? And all you look for is absence of this one edge or presence of this one edge. And you would expect the edge to be there, right? So this is a simpler example that hopefully, it's easier to understand. So you see the posterior probability of this one edge is 0.8. So I'm getting what this plot tells me I should be getting, which is reasonable, right? Okay, so let's move on. So what I try to explain here is how to connect spatial epidemiology with Gaussian graphical models and those two bodies of literature. Well, there's a third body of literature that's ways to be connected with these two, right? And that's ecological inference. So when you look at the count data, that means group level data. So I aggregated the data within each state, right? So now what happens if I have individual level data? Or what happens if I have a combination of individual level data and group level data? If that is the case, then what I need to look at are contingency tables whose entries can only be partially observed and can be subject to other constraint that relates to my group level samples, right? So say this example involves North Carolina. So gender, mother's age at birth, and race are three potential factors that might influence, that might lead to low birth weight, right? So there are 100 counties in North Carolina. So the structure of my data is given by 100 2 to the 4 table, right? Because I made each of those 4 variables to be dichotomous, right? So I have 2 to the 4 tables, and I have 100 of these, right? So the structure of my data looks like this, right? So in each county, I have a 2 to the 4 table, okay? The spatial dependencies are given by this graph in red. We are familiar with it, right? So I don't have any results about this particular data set, but I'm telling you what we should look for, right? So let's take these 2 counties, Wake County and Warren County. Wake County is one of the biggest and more dense populated county in North Carolina, right? And Warren County is one of the poorer and less populated counties, right? So you see that, so you see a very big dark spot in Warren County, and you see a white spot in Wake County. So this is where you have a low percentage of babies with a low birth weight, and in Warren County you have a high percentage, right? So those 2 counties are literally at the opposite end of the spectrum, right? So now see, when you have categorical variables, then you don't necessarily need to look at edges anymore. You can have associations of any order. You can have first order association that involves 2 variables, then you can have second order association that involves 3 variables, and so on. Think about log linear model, right? So just to illustrate how those dependencies can vary, what I did here is I looked for the most likely decomposable log linear models for the Wake and Warren County, right? So the number of recorded births, the sample size in Wake County is this. The sample size in Warren County is hundreds, right? So huge difference here. So you would expect that one model will concentrate most of the probability mass in Wake County because I have so much more information, and I still have a 2 to the 4 table, right? Now in Warren County, see, the sample size is much smaller, so you see the posterior probability of each model. See, I'm more uncertain about what's going on. I'm more uncertain about the relationship, the association that exists in my data, right? The most likely log linear model for the Wake County, see, says that low birth weight is related to race and is related to gender. Those are the interactions that involves LBW, right? And this model really dominates everything else. So I'm pretty certain, given the data I have in Wake County, what my risk factors are, right? Now in Warren County, see, the situation is a bit different. This model right here is the model of independence. So in Warren County, in which I have the highest proportion, very high proportion of low birth weight babies, see, I'm getting that LBW is not related with anything else as the top model. While my second best choice, see, I'm getting race as a possible race factor. So you see, ideally, I would like to construct a joint model in the same way I did with the first data set, right? In which I borrow information across those 100 tables and still, somehow take that discrepancy in the association structure into account, right? So now this is still the simplest version of the problem, and that's the situation in which I actually have individual level samples. But there's a more complicated version in which I also have group level data. So in that case, I have to sample tables, right? Because I don't know the counts that exist in my data, right? So I'll have to sample those counts and input missing data as I go take spatial interaction into account and do this joint analysis, right? So that's what ecological inference is all about, and they, you know, pretty much all they worried about so far are 2x2 tables and, in the best case, I/J tables, right? But now, you know, we can hopefully connect everything and get meaningful results. So if I have 30 seconds, let me just say this. So there's a Bayesian non-parametrics version of our models in which we can actually identify the groups, right? So far I've been telling you about a situation in which I know the groups, state or counties, corresponding with my data, right? And we've been seeing, in the example I just showed you, that the association structure across group can change. What if I don't know the groups? So what if I want to say that somehow my samples can be grouped together such that the same association structure holds? Well, there are ways to do that. So actually identify those subclusters that correspond with the same association structure, and those are some models we have been working on. See, for example, you see here. So this is time series data. So you see you have two regimes, and each regime is associated with a particular graph, and you see how these regimes come and go, right? And we're able to identify these subgroups, right? So anyway, so there are papers on my website. You're welcome to look at them, or the real details are there. Thank you.